All right, folks, welcome back to our discussion of z-scores and the role that they play in our understanding of distributions of scores. So, again, to recap just a little bit from the previous piece, again, we are taking our descriptive statistics that we covered in our previous two modules, our measure of central tendency, the mean, and our measure of variability, the standard deviation, and we are putting them together to essentially standardize this idea of relative standing. So we're putting together a statistic that essentially transforms our mean and our standard deviation into a number that represents the relative standing of each score in a way that, again, is standardized and allows us to compare across totally different distributions with completely different means and standard deviations. Here we see an example of that, two made-up sections of statistics students with different averages and different standard deviations. They even have different maximum number of points. But two students want to compare their scores. We can say who did better overall. Well, that's pretty easy to convert. We represent them both as percentages, and we see that Sarah did better than Nick. But the key question, and again, what we're going to be covering in this module and future ones, is who did better relative to their class, who was higher in their class's distribution. Again, z-scores give us a tool for doing that. They give us a common basis of comparison because you can represent any score in terms of how many standard deviations from average it is. They are powerful. They only require a limited amount of information to make really precise statements about the relative standing of different individual scores. Again, just like we have here, we are only going to have one individual score, one raw score, and just two descriptive statistics about each distribution. And that's all we need. This is like an infomercial here. It's just that easy. All right, so again, z-scores are how we do that. They're how we standardize this information and we turn it into, again, that measure of relative standing. So a z-score is just a number, and it tells us how many standard deviations from the mean was this individual score and in which direction. Positive z-scores, you're above average. Negative z-scores, you're below average. And of course, if you are immediately on the average, your z-score would be, say it out loud, 0. Here's our formula to calculate a z-score. Again, the numerator is our old friend deviation scores. So we take an individual score that we're interested in, we subtract the mean of the sample from it, and we divide by the standard deviation. That tells us how many standard deviations from average our individual score was. So let's calculate an actual z-score, and let's do it for our first student, Sarah. Sarah's raw score, her individual score, is 88. Her section has an average of 80 with a standard deviation of 5. If we wanted to find the z-score, we'd use our formula here. Again, Sarah's individual score is 88 minus 80. Her deviation score is 8. She's 8 points above average for her class. We standardize that by dividing it by the standard deviation, which is 5. We get 1.6. Her z-score is 1.6, and what that means is that she is 1.6 standard deviations above average for her class. So again, it's giving us that valuable piece of information of not just what her score is, but where it falls relative to the average of her data set, her class. So let's say we wanted to take the same formula since we wanted to compare Sarah and Nick. Let's say we wanted to calculate a z-score for Nick. Nick's individual score is 42. Again, his test was worth fewer points. The average score in his class is 35. The standard deviation is 4. So we have new numbers to plug into this formula, but it's the same calculations. We have 42 minus 35. That gives us 7. That's Nick's deviation score. He's 7 points above average for his class. We divide by the standard deviation, which is 4, and we get a z-score of 1.75. That means that Nick is 1.75 standard deviations above average for his class. So we can compare those two. Remember, Sarah's z-score was 1.6, Nick's is 1.75. Even though Nick got a lower percentage of the total points, it looks like his test was a little bit harder, so his relative standing was a bit higher. Relative to his class, he did better than Sarah did. We again can standardize that comparison and say Nick's harder exam, he got a lower percentage overall, but because the exam was more difficult, his class didn't do as well on it, his performance was actually higher in the distribution than Sarah's was. So by standardizing, by calculating these z-scores, we were able to compare Nick and Sarah's scores directly, even though they came from distributions with very different means and standard deviations. So another valuable thing we can do with z-scores is we can reverse the process if we want to. Sometimes we might know our two descriptive statistics, but we might have a z-score that we're interested in instead of an original raw score, an x. So we can reverse the process and find the original score. Let's again use section 1 as an example of that. Mean of 80, standard deviation of 5. Here's our original z-score formula here. Here's how we use algebra to convert it to a form that will let us find an individual score. And all we do is take the z-score, multiply it by the standard deviation. That gives us our deviation score again. It's how many points away from average they are. And then we add the mean to that. So let's say that we have an individual whose z-score is negative 1.2. My animation got away from me there. We say the student is 1.2 standard deviations below average on this test. And that's all we know about them. We can use this second formula here to calculate their z-score, or calculate their raw score, excuse me. They are 1.2 standard deviations below average, and we know that standard deviation is 5, so being 1.2 standard deviations below average means you are 6 points below average. That's their deviation score, negative 6. Then we add that to the mean. They're 6 points below average. The average is 80, so their original score was 74. So again, we can reverse this process and figure out original raw scores based on z-scores that we are interested in. We're going to do a little bit of this sort of thing at a very important part of a future module. So keep this in mind. That's the end for now. Again, next time we are going to come back and talk a little bit about connecting z-scores to the very, very important concept and idea, the normal distribution. Bye for now.